Dear audience, dear students, we will talk in this session about the interaction between the radio waves and the human body. It is in fact a two-way interaction or a two-way effect. The human body affects the radio wave and the radio wave affects the human body. Specifically, the human body is a conductive body that has also dielectric properties. Consequently, the human body can change the radiation pattern of the personal communication device antenna, and also it can change the input impedance, the gain, and other parameters of the device. Personal communication device means devices used by the human beings, such as the mobile telephone, such as the walkie-talkie, the laptop, and so on. Now, this is the effect, or the an idea about the effect of the human body on the personal communication device. Now, from the other side, the electromagnetic wave or the radio wave can couple into the human body, the human tissues, and it can create unwanted issues, unwanted health effects. It may cause unwanted effects. Now we have some numbers here. The radiation efficiency of the personal communication device is reduced due to proximity to the body, to the human body. In particular, the efficiency is reduced, the dipole efficiency. Dipole is, for those who do not know what's the dipole antenna, I will draw here a dipole antenna. It is simply like that. That's the dipole. Dipole antenna. This is a transmission line here, and we have the source on this side if it is transmitting, and this end is open circuit and this end is open circuit, and it has a radiation pattern. The radiation pattern looks like that. Be on the other side, but anyway, let me draw in another color. Just hand drawing. The radiation pattern looks like that. Zero radiation in this direction and maximum radiation in this direction. This is the dipole antenna. It's a wire antenna. It is a wire antenna, and it is widely used in communications. There are many types of this. There are wire antennas, and there are printed antennas on printed circuit boards. Okay, so the dipole antenna efficiency will be reduced to 29% from 100% from large value to 29% near the head, if the antenna is near, if the device is near the head. If the device is near the waist or at the belt level, the efficiency will be reduced to only 15%. The loop antenna is like this. It is a loop. Let me draw it like this. The loop antenna is a transmission line like this, and you have a loop. This is a loop antenna. The current will go in this direction. It will come back in this direction. The current will go around the loop, and radiation will be from the loop antenna. And here the current for the dipole, the current will enter here, and the current will leave here. Of course, the current at the ends here is 0, but here there is distribution depending on the length of the dipole, and also the radiation pattern here also depends on the size or the diameter or the radius of the antenna. The loop antenna efficiency is also decreased. Polarization, cross polarization also occurs if, for example, this dipole has the electric field will be in the theta direction. Assume it's vertical, for example, vertical directed electric field. If the electric field is directed in the vertical direction, if the antenna is near the human body, there would be both vertical and horizontal components. This will be changed, and there will be also another horizontal component. The strength of the horizontal component depends on many factors, in the geometry, on the distance, and other things. So this is the cross polarization. The cross polarization will reduce the capability of the receiving antenna to receive the power. It will reduce this power. Therefore, we will need higher power from the transmitting antenna to reach the receiver. Higher power means higher cost, higher interference, higher harmful effects. Another issue is that the human body exhibits resonance to vertically polarized incident waves. The human body, if this is, for example, the human, okay, let me draw it like this. Just if this is a human here, okay, if this is a human body, now the equivalent length of the human body, when the wave has certain frequencies, the human body will be resonant at these frequencies. Resonant means that the power absorption will be maximum if the frequency or if the wavelength matches the length of the human body. If the wavelength is half wavelength, if the human body length is half of the wavelength, then resonance will occur, or if it is multiple of half wavelength. If the human body is on the ground, the image of the human body here, the human its image, if the human body length along with its image is half the wavelength, then also, or multiples of the half wavelength, then resonance will occur. In this case, the human body will be lambda over 4, or quarter of wavelength, or multiple or integer multiples of this value. As we said, resonance means that power absorption from the wave will be maximum. Also, it was observed that magnetic fields increase near the body. The device near the body, magnetic fields will increase as compared with the case when the device is away from the body. Biological aspects, the skin depth for biological tissues. The skin depth means that the distance through which the wave can essentially penetrate the body. Of course, there are other mechanisms where the wave can penetrate the body. Anyway, delta S is given by K is the propagation constant, which is 2 pi over lambda. Lambda is wavelength, and epsilon r is relative permittivity of or dielectric constant of the human body or the human tissue considered, and sigma is the conductivity of the human body in Siemens per meter, and omega is the radian frequency, which is radian per second, and epsilon naught is the permittivity of free space, which is 10 to minus 9 divided by 36 pi farad per meter, and here minus 1/2 exponent. The impedance of biological material is low, ranges between 38, typical values between 38 and 57 ohms for frequencies between 100 megahertz and 3000 megahertz or 3 gigahertz. This plot shows the impedance of a dipole, or the impedance of the wave impedance near a dipole. The wave impedance near a dipole. If we are in the far field, K is the propagation constant, R is the distance from the dipole or the loop antenna. If K is greater than, say, 5 here, if it is greater than 5, if we are a little bit far away from the antenna, the small dipole or a small loop antenna will the wave impedance will be constant. They will have similar wave impedances of about 377 ohm or 120 pi ohm. If the distance, if you are close to the antenna, the wave impedance will be small for the loop antenna, and it will be high for the dipole antenna, because the dipole is an open circuit at its ends, and the small loop is a short circuit for DC. Of course, for AC it is not. It is a little bit different. As we said, that the wave impedance for the loop and dipole antennas are almost equal for KR greater than 5. Antennas are usually close to the human body, so the loop antenna impedance will be low, and the dipole impedance antenna will be high, and consequently the loop antenna better matches the impedance, the low impedance of the human tissues, human body. To explain now the concept of specific absorption rate, SAR, which is measured in watts per kilogram of kilogram of the human body tissues, or the biological tissues, whether it is any human body or animal or a tree. Now SAR is the time rate or derivative of the energy absorbed by the tissues with respect to the mass. As you can see, energy over time is power, and power over mass is power per mass. This is equal J dot E over rho. J is the current volume, current density, dot product with the electric field vector, and J equals sigma E. So sigma dot E is E squared. So this would be sigma E squared, and rho is the mass density of the tissues measured in kilogram per meter cubed. So this is the equation of this R. Sigma the conductivity, and E is the electric field, and rho is the mass density. The mass density of water, for example, because the human body or the living tissues are mostly composed of water, 3/4 of the body is water. Rho is about 1,000 kilogram per meter cubed. 1 ton per meter cube. The temperature rise, to find the temperature rise, of course, as the effect of the waves on the human body or in the living tissues has two categories: thermal effects and non or athermal effects. If we want to consider the thermal effects here, then S, the absorbed power density, S, is given by this equation. Rho, as we said, is the mass density, and C is the specific heat of absorbing medium in joule per kilogram per centigrade, and T is the exposure time, and delta T is the temperature rise in centigrades in the living tissues. Okay. So SAR is equal, just if you remove rho from here, the remaining thing will be SAR. Here, this is SAR. This is specific absorption in watt per kilogram, and this is in watt per meter cubed. So SAR is equal C delta T over T. T time period, and delta T is the temperature rise. Okay. There are radio frequency exposure standards adopted by the World Health Organization, and also adopted or with some variations by many countries over all the world. Now let's talk about the natural sources of electromagnetic fields. The sun, the light is a form of electromagnetic field. It has electric and magnetic fields. It will give 130 milliwatt per centimeter squared at all frequencies. Of course, you cannot stay for a long time under the sun, direct sunlight, because this will severely harm you. Thunderstorms is another source, natural source for electromagnetic fields. It will give volts, several volts per meter away from it, of course, not direct under the thunderstorm. The Earth magnetic field, also it is essentially a static magnetic field of the order of 40 ampere per meter, or the magnetic flux density is about 50 microtesla. Man-made fields, unfortunately, produce much higher intensities and with different spectral distribution, with different frequencies. It has different frequencies and higher densities, higher intensities. Now the external electromagnetic fields can couple into the human body, and it couples most efficiently when the field is aligned with the body axis at half-wave resonance range, as we mentioned here. There is a human body here. You can see over the ground. This is the ground. This is the ground. If the wave frequency is such that the height of the human body is lambda over 4, a quarter of lambda, the image here will be also quarter of lambda, and the total length here will be lambda over 2. If lambda over 2, lambda over 4 here is equal the effective length of the body. The effective is around 2 meter. Maybe the typical value is height of a human body is 1.7 meter, but the effective is around 2 meter. Now multiply 4 by 2, therefore lambda is 8 meter. When lambda is 8 meter, this body on a ground is resonant, which means that the power absorption will be maximum from the wave. To find the corresponding frequency, we divide the speed of light, because in free space, over the wavelength, which is 8. This gives 37.5 megahertz. At this frequency, the human body, of course, the height of the human body, the material, specific material that the human body is composed of, I mean the material parameters, makes that different bodies will resonate at different frequencies. If the body is isolated from the ground, then the lambda over 2 will make resonance. In this case, the frequency will be double this. It will be double this times 2, and this will give 75. 37.5 times 2, 75 megahertz. Your body will be resonating at this frequency. For infants, the resonant frequency is higher because the infant's length is smaller. So if the infant equivalent length is 1 meter, let's say, if the length is 1 meter, sorry, and or say it's half a meter, say it's half a meter, and it is equal lambda over 2 for resonance. This means that lambda is equal to meter. And the frequency is equal c of light 3 times 10 to 8 meters per second over length, which is 1 meter, and this is 300 megahertz. 3 times 10 to 8 is 300 times 10 to 6, which is 300 megahertz. Megahertz here. This is the number here, 300 megahertz. The lowest resonant frequency is about 30, let's say it's about 30, and the highest is about 300 megahertz for a human body, for the whole human body. In addition to that, not only the whole body resonate with the frequency or with the wave, also body parts can resonate also. The adult head can resonate at 400 megahertz, and the baby head can resonate at 700 megahertz, because the body head is a cavity. In electrical engineering, or the wave sees the human head as a cavity, the human heart as another cavity, the human chest a cavity, and so on. And these cavities will resonate at different frequencies. This is a human head. This width here is about 16 to 18 centimeter, and let's see the relation between this distance and the cellular telephones, mobile frequencies. Mobile frequencies are either 900 megahertz or 1800 megahertz. At 900 megahertz, the wavelength is the speed of light over the frequency. 900 is 9 10 to 8, and we will obtain 1 over 3 meter the wavelength, and half wavelength is 16.7. So the cellular phone frequency is resonating with the width of the a human head, because this is lambda over 2, and this and also at 1800 megahertz the wavelength will be half of this distance, half of the 33.3, which is 16.7, and also since it is a multiple of this, it will also resonate, or the human head will resonate in general at both mobile frequencies. At this situation, the absorption will be higher, the body absorption will be higher, and the performance of the antenna will be deteriorating, which requires more power from the antenna, from the mobile telephone, and this will adversely affect the human head, human body. Now, the exposure guidelines and regulations, they distinguish between two cases or two environments. An environment is called the controlled environment and uncontrolled environment. Controlled is defined as an environment in which the persons are fully aware of the potential for exposure and can exercise control over their exposure. So two conditions are required for a person or a party to be considered controlled. The person should know the adverse effects of the electromagnetic fields and how they couple into his body and their adverse effects. And second condition is that he can change the situation. He can move from exposure. He can reduce the exposure. He can exercise control over the exposure. In this case, he is said to be controlled environment, or he is said to be in a controlled environment. Now, uncontrolled environment, in which if any of these conditions is violated, then it is uncontrolled environment. If the human body does not know about the harmful effects, then it is uncontrolled, uncontrolled environment, public exposure. If he knows about the adverse effects of the electromagnetic fields on his body, but he cannot exercise control to reduce the exposure, he cannot do anything, then also he is considered to be general public uncontrolled environment. Now, this is the existing specifications agree in the basic limits for the whole body, but but they do not agree in the local peak SARS. For the whole body, they agree it is the same value. And just to mention that the international regulation, they consider only the thermal effects. They do not consider the non-thermal effects, unfortunately. Okay, we will start. This is general figure for effects. As you can see here, this is the maximum radiation density of the electromagnetic field which a human can be exposed to. The limit is lower for 30 to 300 megahertz, as we said, because this is at these frequencies the human body will be resonant and the absorption will be maximum. So the limit here is lower. And away from this frequency range, the limit is resonance, possible resonance. Resonance of the wave of the human body. Away from this region, the wave is possibly not resonant, but it can also resonate with the human head, with the human heart, with the human kidneys. So anyway, now the controlled environment, because the person here he knows about the harmful effects of the waves, and he can exercise control over his environment. He can reduce the exposure. The exposure limit is higher. For the general public or uncontrolled, if he does not know about the harmful effects of the waves, or if he knows but he cannot make any changes, then the limit is lower. this frequency in megahertz. Now how to calculate the electric field? RMS value is the x component squared plus the y component squared plus the z component squared under square root. It is the magnitude of the electric field in RMS value, root mean square. Because the electric field is a vector. It has three-dimensional vector. It has components. It has x component, y component, z component. And similar thing can be said about the magnetic field. It is a three-dimensional vector and it has components x, y, and z components. Can be measured, of course, by probes. The radiation power density is given by this equation. The electric field squared, magnitude squared, over eta naught. Eta naught is the impedance, wave impedance of the free space, which is 120 pi. This is 120 pi 3.14 ohm, which is equal to around 377 ohm. 377 ohms. Okay. This is in watt per meter squared. This power density, radiation power density. Now, if we want to convert this in terms of, instead of watt per meter squared, we want it in milliwatt per centimeter squared. As we know that watt is 10 to 3 milliwatt, 1000 milliwatt, and meter squared is 10 to 4 centimeter squared, because 1 meter is 100 centimeter. 1 meter squared is 10 to 4, 10,000 centimeter squared. So watt is 10 to 3 here, milliwatt, and meter squared is 10 to 4 centimeter squared. 10 to 3 over 10 to 4 is 0.1. So this is 0.1 e squared over eta naught. If we use this equation, we can directly get the answer in milliwatt per centimeter squared. If we use this equation, we get the answer in watt per meter squared. And here, instead of we substitute 377 for eta naught, and point as is here as it. This is e squared is the x component squared plus y squared plus z squared, e squared. Similar thing can be said about the magnetic field. The power density in terms, the surface power density of the wave in terms of the magnetic field is given by this equation, 0.1, same, e squared magnitude over times here, it will be times eta naught, not division, times eta naught. In the far field, the power density calculated, surface power, radiation power density calculated from the electric field or magnetic field, you will get the same answer. But in the near field, they will have different values. So we take the maximum of the power derived or computed from the electric field or from the magnetic field or measured. If we have mixed frequency fields, fields that have different frequencies, many frequencies, if you are exposed to many frequencies, and normally we are exposed to many frequencies, we have radiation from the mobile towers, we have radiation from the mobile phones, we have radiation from the Wi-Fi, we have radiation from the electrical equipment, we have radiation from radars, we have radiation from, as you know, many antennas are surrounding us and they are immersing the medium around us with waves that has different frequencies. So how to calculate the exposure when you have different frequencies, fields that have different frequencies? We use this equation. Summation of I1 to n. N is the total number of sources of electromagnetic field around you, and Li is the limit. This is the limit of the power density, radiation power density, and this is the actual power density. So S1 over L1. L1 is the limit for a certain frequency, and this is the actual exposure at this frequency. For the second frequency, we take the limit at the second frequency, and this can be taken from the tables of the exposure standards or exposure. And this is the calculated or measured from, and so on. The total here should be less than 1. If it is less than 1, then the exposure is okay, and if it is greater than 1, the exposure is not okay. I remember that these equations are based on only the thermal effects. They do not consider the non-thermal effects of the electromagnetic fields. Okay, here is an example. Electromagnetic fields at a location from 4 antennas. Assume that you are exposed to 4 antennas. With the first antenna, electric field is 33 volt per meter at a frequency of 18.1 megahertz, and the second is 20 volt per meter, the electric field, at 47 megahertz, and we have also 15 volt per meter from at 152 megahertz, and the fourth antenna gives, or the fourth source gives, 1 volt per meter at 460 megahertz. We want to make sure to know to examine this equation if it is greater or less than 1 for this case. Now we take the limits from here from tables given here. Here the occupational or controlled environment, as we explained, and we have also the uncontrolled general public population or uncontrolled. Now we take both cases. As you can see here, the power density is 900 over f squared for the range between 3 and 30 megahertz, and it is between 300 and 1500. It is f over the frequency over 300, and f is in megahertz, of course. And for general population, we have between 1.3 and 30 megahertz, it is 18 over f squared, the frequency squared, and for 300 to 1500 megahertz, it is f over 1500. Let's calculate now. You can see. So we said that for between under 30 megahertz, it was 900 over the frequency squared. The frequency is 18.1, so we put 18.1 squared, and we get 2.7 milliwatt per centimeter squared. And F2, at F2, it was fixed. It was 1 milliwatt per centimeter squared from the table, and at 152 it was fixed also 1 milliwatt per centimeter squared. At 460, it is greater than 300. The equation was the frequency over 300. The frequency is 460 over 300. We get 1.53. Now we calculate. Those are the limits. Now we calculate the S, S1, S2, S3, S4. S is given by 0.1 electric field squared over the impedance of a free space, which is wave impedance 77 ohm. We put here the field was here 33, 20, 15, 1. We have here, as you can see, 33 squared, 20 squared, 15 squared, and 1 squared. This is the 1 is the field measured near the person from the fourth antenna, and we get these results. Now we divide this by this plus this by this plus this divided by this plus this divided by this, as we can see, by this, and we get this, and the exposure is acceptable because the combined densities did not exceed the maximum permissible exposure limits. I will stop here and we will continue later.